So as Kate told you, my name is Dario and I'm a third-year PhD student at the Leiden University. Today we will talk about PAHs, and specifically PAHs in the interstellar medium, but also in a solar system. And we will look a bit more about also a mineral that is quite ubiquitous in all rocky parts in the universe that is called Forsterite. But first of all, I would like to introduce a bit myself. So Katie already told you that I come from Palermo. That is a town in Sicily, in Italy. And here I got my master in bachelor in chemistry. In my bachelor and master in chemistry. And during my master, I approach quantum chemical methods to model catalysts like boron nitride nanoflakes. Here you see a sample of a boron nitride nanoflake. And I will not go into deep in this topic because this is not the aim of this webinar. But if you're interested, you can actually read a bit more our recent publication about boron nitride. After Sicily, I moved in Leiden, that is a town in the west part of Holland, 50 kilometers away from Amsterdam, and I joined to Leiden University in the Leiden Observatory. This actually this building over here in this picture. And I'm also one of the 16 early stage researchers, they call us ESRs, of a European network called Europa. Europa has the aim to study PAHs, the chemical physical properties of PAHs in space, but also in terrestrial environment, and it is funded by the EU. And before I forget to acknowledge all people that contributed to my PhD studies, I would like to thank my supervisor's team, but also all my co-workers and all people that spend time with me on contributing to define my current project about Forsterite. Thank you to Claudia for the revision of this webinar, and thank you to all, thanks to all Europa Network. So today we are talking about polycyclic aromatic hydrocarbons. Those are carbon-bearing molecules like this one. This is a sample of coronine, that where we have here the violet balls are carbon atoms and the white balls are hydrogen atoms. And those molecules are quite ubiquitous in space. They're important because when they interact with UV photons and the light, they start to vibrate, exactly how right now coronine is doing. And the vibrational modes cause the emission of important infrared signatures that then the astronomer needs in order to probe the universe. Exactly where all carbon is locked up, which are the species that act as a reservoir for carbon. One is the simple molecule, CO. The 1% of the carbon is locked up in CO, and the 15% of the carbon is locked up in PAHs. We can think that those two molecules are the starting point to build more complex molecules. We can start, for example, from a simple molecule like CO, and then we can think to build up more complex molecule from CO, or we can start from a large molecule like PAHs and fragment those PAHs due to the radicals and also the UV photons coming from, for example, from a bright star. And then those little species eventually will be incorporated in a cometesimal and planetesimal and delivered from the interstellar medium to solar system objects. But PAHs, as I told you, are really important species for astronomers, and we know from observational infrared spectra, like this one, that those species are in the interstellar medium. For who doesn't know what is interstellar medium, is actually the space between the stars. If we check the infrared spectrum between the region of 11 and 14 micrometers, that is the region of the CH bending of PAHs, we can actually see the appearance of these peaks that tell us a bit more about the structure of these PAHs, but not just the structures, also the charge of these PAHs, if they are neutrals or, for example, cation. But for the aim of this webinar, we will focus just on neutral PAHs. And we see here a dominant peak around 11 micrometers, and these peaks belong to the CH bending of so-called solo carbons. The solo carbons are carbons that are bound with one hydrogen, and are all these rings over here, that they are also called zigzag edges. And we will see that zigzag edges play an important role, especially for molecular hydrogen formation. But also we have other kind of peaks over here between 12 and 30 micrometers. These peaks belong to so-called armature edges, where we have an aromatic ring with two carbon bound with two hydrogens. And then these little guys over here belongs to the trio, when we have three hydrogens bound on the aromatic ring, and when we have four hydrogens bound to the aromatic ring. And actually, these quartet carbons play an important role on Forsterite, and we will see later on. But why exactly we need to study molecules in space? Why we need this? We need this because molecules interact with the UV photons, interact with the radiation in space, and then the emission. It's important for astronomers because tell us not just about the chemical structure, but also the physical properties, also important information like the temperature where those molecules are. And here in red, we have actually two important key questions that I'm trying to address during my PhD studies, and is how polycyclic aromatic hydrocarbons are connected on building the so-called organic inventory in space, and exactly how those paths from the interstellar medium are delivered in solar system objects. And the aim, as Kate also told you, of my PhD studies is to understand how PAHs can act as interstellar catalysts. I studied in my first two projects how those molecules are hydrogenated, and then they catalyze the molecular hydrogen. And my current project, I'm focusing on paths in minerals as Forsterite. We will see a bit more about this topic. But first of all, how we explore the universe. So what are the subjects that we need to use in order to explore the universe? So we have three branches. One is physical chemistry, and this is actually my branch. And then we have also astronomical observations, astrochemical modeling. I'm focusing on the physical chemical properties of molecules, but sometimes we need also get information from astronomical observation and astrochemical modeling. I'm doing this using a method that is called density functional theory. Is an approximate method able to solve the Schrödinger question of a complex molecule. So we know how to solve exactly this equation for example, hydrogen. But in order to solve this equation for complex molecule, we need to use approximate methods like DFT. And this question is important because contain all the physical information that we need to, in order to understand the chemical reactivity and the physical properties of this species. And we start, for example, from an initial guess where we think that those two water molecules are bound on the surface. So we think that this is the correct configuration with lower energy, where these molecules are bound on the surface. But then when we solve the Schrödinger question for this initial guess, sometimes things reactivity can take place. For example, one of the water molecules can react with other atoms on the surface and then dissociate. So this is just an example how important it is to solve this Schrödinger equation to get the correct information. And now I will show you a bit more what I've done in my first two projects. Specifically, we are going to focus on PAHs in gas phase and how they can act as a catalyst for H2 formation. Why we think that they can act as a catalyst? Because PAHs like this one is coronin, act as a surface, and they can host atomic hydrogen on the surface, as I'm showing in this slide. And those are called HydroPAHs. HydroPAHs might play a role in the formation of molecular hydrogen. And we know also that those PAHs are present in the interstellar medium thanks to observations like this one. We have the observation of the Orion bar between 3.2 and 3.7 micrometers. Here we see that we have a broad peak related to the aromatic CH stretching of of PAHs. So we know that those PAHs are mainly aromatic, but we also notice these little peaks over here that belongs to the aliphatic CH stretching. So part of this PAHs must be also hydrogenated. If we, for example, we record the infrared spectra of hydropyrene in lab, we see the appearance of these peaks that match quite well with observations. So we know that part of this PAH must be hydrogenated in the interstellar medium. But why molecular hydrogen is so important, especially for astronomers? Because molecular hydrogen is the most abundant molecule in the universe. It is responsible of star formation, and also it's quite ubiquitous at present in regions called photodissociation regions. Here I'm showing a picture of a photodissociation region in the Orion. And we know that this region is quite concentrated of UV photons. In principle, we must not have any hydrogen-hydrogen bond. But astronomers actually saw the presence of molecular hydrogen in this region. How is possible that? We know that PAHs can be hydrated, so can host these atomic hydrogens on the surface, and then those atomic hydrogen can combine to form a molecular hydrogen, and this is called PAH hypothesis. But also we know that dust can play a role, but the difference between PAHs and dust is that dust is not able to completely absorb the UV photons, and therefore we have a hot layer on the surface of the dust that doesn't allow a chemical bond between those hydrogens and the dust surface. So therefore PAHs must be an efficient catalyst for molecular hydrogen formation. And this is my first article that I published in PCCP, where I studied pentasine. Pentasine is a linear pi molecule with 5 aromatic rings, and is one of the representative PAH with so-called zigzag edges, the solo carbons. And the rule of this project was to understand the hydrogenation sequence of pentasine and the reactivity of solo carbons. And we did that not just with DFT, but also we approached the experiments conducted by Lew Orniker in Aarhus University and co-workers, where they expose a layer of pentasine to a hot beam of hydrogen flux. And we see the spending time, there are the appearance of species with 2, 4, 6, 10, 16, and 22 extra hydrogen chemisorb on the surface. And those are called magic numbers. Therefore, HydroPAHs are equal to magic numbers. And we don't explain why we had this specific sequence, but we don't find in the mass spectra species like 18H pentasine or 12H pentasine. So we must use a different approach to understand better why we see this specific sequence of HydroPAHs. So first of all, we need to understand the hydrogenation sequence, and we use DFT approach, and we need to model the one single pentasene molecule in gas phase. In order to do so, we use a code that is called Gaussian 16. And here I calculated the binding energy when one hydrogen is chemisorbed on these different types of carbons. We can see the binding energy as basically a property that we need to measure in order to understand how strong these hydrogens bind with carbons. And we know that, for example, the inner carbons of the ring, they don't play an important role on the chemisorption of these hydrogens, but the solo carbons of the central ring, also this lateral ring, have more important role in this process. And after we hydrogenate one side, we create basically a perfect radical path because we have unpaired electrons. So an electron is not paired with any other electrons. And this is localized in the central ring, but just not in the central ring, since everything is connected, it might be sometimes localized in different rings. But this effect is less important as far as we go from the hydrogenated side. We know for sure that the strongest binding is with the adjacent carbons that are called orthopositions, or the opposite position respect to the hydrogenated side, that is called paraposition. So we know that we expect this hydrogen attached in one of these carbons over here. And this is the sequence that I found using DFT methods. And I noticed that the pentasene trying to preserve as long as possible the aromaticity of the system. And specifically, that means that first we hydrogenated the central ring and we try to preserve the aromaticity, and then the hydrogenation is spread from the center to lateral rings. But we didn't explain yet why we see these magic numbers in the mass spectra, because something called activation energy play an important role. So if we think that we walk on the street and at a certain point we meet a barrier, so an obstacle that we need to overcome, so how much energy I need in order to jump and overcome this barrier. This is exactly the concept of activation energy, how much energy we need in order to overcome a barrier to form one single hydrogenated pentasene. So in the case of pentasene, for the first hydrogenation, we need just 0.08 eV. That is quite a low barrier compared, for example, to the hydrogenation of one of the two duocarbons of coronin, where we need 0.19 eV. That means that we have a difference of reactivity of 11 millieV respect to the duocarbon. And after we hydrogenated with one extra hydrogen, the pentasene, it's easy to add a second hydrogen to a barrierless reaction because it's a radical reaction. But the problem occurs when we need to overcome exactly all these barriers over here that are above this line, the red line. So all barriers that are higher than 0.16 eV. And those are exactly the barrier that we need in order to add another hydrogen to the 2H pentasene, 4, 6, 10, 16 pentasene. And then we have also, as a magic number, 22 hydrogens attached on pentasene, because this is the maximum number of hydrogen the pentasene is able to host. So in order to add a third hydrogen, we need to overcome a huge barrier. And at a certain point in the experimental condition, in the experiment, we are able to overcome all this barrier. But since the barrier is quite large, those species have a long lifetime, and therefore we are able to detect them. But we are not able to detect magic numbers like exactly like the 8H pentasene, because this barrier is lower, and so it's easy in experimental condition to overcome this barrier, forming other species. And also, besides pentacene, we studied in another article published in PCCP, pyrene molecule. Specifically, we focus on defective PAHs and a certain type of defect called Stonewall's defect. If we think that basically PAHs are usually formed by hexagonal rings, and we need to rotate one of these hydrogen carbons over here, then we can form a different type of structure like 2,7 and 2,5 member rings. So this is called Stonewall's defect because Professor Stone and Professor Wells discovered first this type of defect. And we use both molecules to understand the catalytic properties of pyrene for molecular hydrogen formation purpose. So here we have the intrinsic reaction coordinate that I found out with DFT. Here we have the mechanism for the addition of hydrogens to pristine pyrene, so a pyrene with hexagons, in order to form a molecular hydrogen. So if we hydrogenate one of these carbon of pyrene, we need to overcome a barrier of 0.22 eV in order to form this radical that has higher energy, and then it's quite easy and barrierless to form a species with 2 hydrogens attached on pyrene. But then if we want to extract these hydrogens, we need to overcome a barrier of 4.21 eV. That is quite huge, especially in interstellar conditions. But exactly what happens if we have the defect? If we have the defect, the first hydrogenation is a bit lower than the pristine one, and then it's quite easy and more stable to form these intermediates with a difference respect to the pristine one of exactly 0.11 eV. And then, in order to extract those 2 atomic hydrogen, to combine those 2 atomic hydrogen to form molecular hydrogen, we need to overcome a lower barrier of 1.85 eV. That means the Stonewalls play a catalytic activity for molecular hydrogen formation, and this is actually the definition of a catalyst. Catalyst can be anything, able to reduce the amount of energy that we need to trigger the reaction, that usually we need to trigger the reaction. And then the cycle, the catalytic cycle, can occur again, since after we extract molecular hydrogen, we can again hydrogenate Stonewalls and re-extract again molecular hydrogen. So in summary, this is what I've done in my first 2 projects during my PhD studies. I basically shed light on the reactivity of solo carbons, and we found out that magic numbers are limited by the activation energies rather than the binding energies. And also the defects play an important role because they enhance the reactivity of the species, and HydroPAHs must be important intermediates for molecular hydrogen formation. And now, how exactly those PAHs from interstellar medium are delivered in solar system objects? And here we try to understand that absorbing PAHs on Forsterite mineral. And what is exactly Forsterite? Forsterite is magnesium silicate, and this mineral is present in protoplanetary disk, planets, comets, meteorites, also dust, in every type of rocky parts in the universe. And we know the specific type of material called carbonaceous chondrites, specifically carbonaceous chondrites meteorites, like this one in this picture, contain both Forsterite and polycyclic aromatic hydrocarbons. And they're called carbonaceous because those meteorites contain also not just PAHs, but many type of organic matter like amino acids. And they are called chondrites because the inorganic part, so the not organic part, is basically represented here in a spherical shape that is called chondrulus. That is the reason why we call it carbonaceous chondrites. And the key questions are how PAHs are basically captured by Forsterite. So how strong is this interaction? How the catalytic activities of PAHs change in solid state? How these PAHs are somehow connected with prebiotic building blocks of life. In order to do so, we need to use different approaches. And that means we need to use a different codes. What we are going to use in order to model a surface in solid state, we use periodic density fractional theory. But first of all, we need to study the properties of the mineral before to absorb PAHs. And we did that using a really expensive but accurate code called VASP, Vienna Binisium Simulation Package. And we use metadis in order to produce different surfaces of Forsterite. Here I reported the theoretical methods that I use. I know that today the audience is quite broad because we have also astronomers, so I will not go into deep in the theoretical methods, but I reported them in the slide if someone is curious about the theoretical approaches. And then in order to absorb big PAHs, we need to change code because VASP is too computational demanding. So we need to use a less expensive code called Siesta. And we use also an approach that is called the DFT-D4 because usually density fractional theory doesn't take into account long-range interactions like van der Waals interaction, electrostatic interaction. Therefore, we need to add so-called D4 that was implemented by Professor Grime in order to take into account those long interaction energies. So Forsterite is exactly this mineral that I already told you, and in order to model the mineral, we need to put the silicate and magnesium in a box that is called unicell. So we can think that Forsterite is basically built up by magnesium atoms that are octahedral coordinated with 8 oxygens, and with silicons, and silicons are coordinated with 4 oxygens. And we know that in total the mineral is neutral because we maintain the neutral balance of the mineral, but we know that the crystal is quite ionic because the magnesium are cations. We have magnesium 2+, and the silicates are anions, specifically 2-. So we optimize the structure of the bulk of Forsterite, but we need also to optimize the length of the unicell because we need to find the proper length that allow us to model Forsterite with the lowest energies as possible. We did that with DFT-D3 methods, and here I reported the optimized unicell that I found during my calculations. And this unicell, we can see that I basically reproduce the same values or similar values than other previous studies like Prijov and other experimental studies over here. After we study the bulk of Forsterite, we need to create different Forsterite surfaces. Here, these values here are called Miller index surfaces, and based on how we cut the bulk, we can create many different types of surfaces. And we can also construct so-called morphology construction. So we can predict actually how Forsterite crystallize in the real life. And this is actually a good example because I reported here the theoretical crystal that I found with DFT methods. And here I reported an example, a picture of a real Forsterite crystal. And here, there is just a part of the crystal. We are facing right now the 010 surface as we are watching the crystal from the top. So here we have the 010 surface. And then here we can see the 100 surface, that is the surface with lower area sites and also with lower energy. And then we have 101 and 001, exactly how we predicted with DFT methods. After that, in order to accommodate on the surface large PAHs, we need to enlarge the unit cell. And we created that 010 Forsterite. We picked the 010 because it's the most stable in energy, also have a larger area. And we basically enlarged the unit cell. I reported here the new values of unit cell, creating so-called supercell, where we accommodated 336 atoms inside this box. And in order to model the interaction of PAHs on Forsterite, we use a less expensive code called Siesta that is developed using localized atomic orbitals that allow us to model fast big systems. And on top of that, we also created different types of surfaces. One, when we replace one magnesium atom with iron, another one when we replace magnesium atoms with nickel, and also a surface where we removed a magnesium oxide atom, creating a perfect neutral vacancy on the surface. We created those called point defects because we know that defects are intrinsic in materials, specifically in minerals, during their synthesis. And also we know that iron, nickel, vacancies are present in Forsterite in lower concentrations. So we model also three surfaces, and then we decided to absorb on a pristine 010 surface, that one where we have an atomic iron, nickel, and magnesium oxide vacancy. We absorb different type of PAHs, starting from naphthalene, anthracene, fluorantine, pyrene, coronin, and benzocoronin. So those are all PAHs with different sites, with different number of aromatic rings. And we calculate so-called absorption energy. And we can convert this absorption energy in binding energy if we just think this number as a positive. Therefore, we can see here the absorption trend of this PAHs. And the first thing that we notice is the vacancy as the stronger interaction with all PAHs, specifically also with benzocoronin, where we have a binding energy up to 5 eV. And then the trend is the iron bearing surface is acting stronger than nickel and then the pristine. So we know that this is the trend of interaction, but exactly why is that? Why we have these strong interactions, specifically with the vacancy? We need to look a little bit more in detail the geometries and also the electronic structure of this molecule. Here, for example, we have the optimized geometry of coronin absorbed on Forsterite surface. And here we have coronin on the vacancy of Forsterite surface. And we see that the structure is no longer planar, as usually we have with PAHs in the gas phase. In the gas phase, those PAHs are usually planar. But in the case of Forsterite, we have a distortion in the structure. Also here in the vacancy, coronin is completely curvated. Why is that? If we check the distance magnesium carbon atoms, we see this value that since in the range of a bond between carbon and magnesium atoms. And in order to understand exactly which type of interaction we have, we need to use an approach that is called crystal orbital overlapping population, COOP. And this approach tells us if this interaction, for example, is dominated by bonding, no bonding, or anti-bonding interaction. Using these methods, we know that all aromatic rings of every PAH that we absorb on the surface are dominated by bonding interaction with magnesium atoms. That means that we have a coordination of the pi system with the magnesium atoms. And if we have also a transition metal on the surface, like iron or nickel, the binding energy increase respect to a pristine one. Why this binding energy increase? Because besides having the coordination of magnesium atoms with the lateral pi systems in those molecules, we have also the coordination with the transition metals. That is the reason why the binding energy increase. But we don't explain why we have the strongest binding energy for the vacancy. For the vacancy, we need to understand if we can create a bond or not. So we notice that the quartet rings in every PAH, not just this PAH that is called benzocoronin, interact strongly with the vacancy surface, creating two covalent bonds, carbon-silicon bond and carbon-oxygen bond, consuming the aromaticity of the quartet ring. This is the reason why we have a stronger binding energy with all those PAHs that have quartet rings in their structures. But also, besides the covalent interaction, we have also the coordination of magnesium atoms with the lateral pi systems. And in the case of benzocoronin, we found out also this structure over here. This structure is exactly the structure that's causing this large binding energy up to 5 eV, because besides to create a covalent bond carbon-silicon bond, we have the dissociation of one hydrogen and the transposition of this hydrogen in one of the oxygen in the vacancy. This is exactly the reason why we have a stronger binding energy. But after we analyze the trend of this binding energy, we know that larger PAHs are easily delivered from the interstellar medium to solar system object, because more we increase the aromatic rings, that means more coordination and larger binding energies. But we don't explain why in the experiments the small PAHs have larger abundance than big PAHs. For example, here I reported this study conducted by this guy over here and collaborators, where they calculated the abundance of Murchison and Lone meteorites. That are two types of carbonaceous chondrites. And we see here that PAHs with 2, 3, 4 aromatic rings have a larger abundance than PAHs with 5 and 6 aromatic rings. But actually, we are able to explain this using the binding energy analysis, because if the PAHs are larger, the strong bind on the surface, that means that it's more difficult to detect them in experimental condition. So in conclusion, we study PAHs in the interstellar medium as a potential catalyst for molecular hydrogen formation. We know that defects in every kind of material, not just in molecules like PAHs, but also in minerals, play an important role because they enhance the reactivity of the material. And we know that PAHs strongly bind on the surface because the coordination with magnesium atoms and also with transition metals atoms, and also the geometry of the PAH change on the surface. That implies also the catalytic activity must change when we support those catalysts on the mineral. And in the case of the vacancy, we have also the formation of covalence bond, and this causing the strong binding with the quartet carbons. And yeah, this is how exactly DFT can help us to understand more the molecular properties in interstellar cosmochemical conditions. And just to give you a hint how powerful is this tool, almost everything. And right now I'm modeling the chemisoptional fullerene on the vacancy, this is exactly the optimized geometry that I found out a few days ago. And the aim, the next step of this project would be to understand how the catalytic properties of this PAH help to form building blocks of life like amino acids. Thank you for your attention. Kate?
Hi, yes. So you can go ahead and open the chat at the I think it should be at the bottom of your screen to see questions from everybody.
Do I need to stop my sharing?
You can stop or you can keep it on your slides in case people have questions about them.
Okay. Because right now I'm not able to see this. Yeah, because I'm in presentation. 1 second. So, okay, I have the chat over here. Thank you, Dana, Rodrigo, and Mattes. There is actually a question over here. Did I understand correctly that a magnesium side vacancy was made by removing a magnesium atom and an oxygen atom? Did you study the effect of oxygen vacancy formed by only removing an oxygen atom? So yes, you understood correctly. I removed magnesium oxide vacancy. I didn't study the oxygen vacancy because in literature is not an important vacancy for the case of Forsterite. Another important vacancy in the case of Forsterite is the magnesium vacancy, but we prefer to have a so-called Schottky defect, like the magnesium oxide vacancy, because in this way we maintain the neutrality of the system. So it was more easy for us to model this type of defect. Any other questions? So Chris, nice presentation. I'm curious why specifically M062X PCSEG1 was chosen to model the H2 formation of pentasyn. Were there any other levels of theory and basis set used to study this, and did they give comparable results? How does this level of theory do a predicting energy barriers and handling aromaticity? So the M062X was actually benchmarked by Rocco Martinazzo group in Milan University. That is also my co-worker. Instead, I benchmark the basis set. So we chose M062X because have if I remember correctly, the 54% of exchange are trifoc. So it's a meta GGA, and with benchmark we also more accurate functionals. We also try to have a full exchange part from R3FOC, so the M06HF. We also try other different hybrid functionals, and we saw that M062X was the only functional able to reproduce accurately the binding energy and the activation energy compared to Kappa cluster, but also to data set that we find related to thermochemistry. So M062X is the faster one, able to accurately reproduce binding energies, activation energies, compared to other functionals that, yes, they can also accurately reproduce those binding energy, activation energies, but they are more costly, expensive. Instead, I chose PCSEG1 because PCSEG1 is a polarized, consistent, segmented double-Z basis set. This basis set basically was optimized for DFT. So this basis set was developed to converge the density functional. And I also benchmarked this basis set with CCPVDZ, also the POP basis set. All of them, they gave the same result, but I decided to use this specific basis set because I had easy convergence, especially when I increase the distance between the hydrogens and the carbon atoms. I hope that I explain everything. Also, Mariette has a question. Thank you for the very interesting presentation. Have you considered focusing on surfaces and defects with weaker absorption? This will help catalysis needs less strong absorption and disembarking the space shuttle. Exactly which kind of defects are you have in mind, Mariette? Any type of defects. So the thing is that we don't want to study the catalytic properties of the mineral, but of the PAHs. So the mineral acts as a support for those PAHs. The actual catalyst is the PAH. And we don't actually know which are the what are the catalytic properties of PAHs, because this is the aim for the next project. So we just noticed that, for example, atomic hydrogen are strongly bonded on PAHs when they are chemisorphed on the surface, but we don't know yet how is able to catalyze, for example, a glycine or other type of amino acids. So we don't really want to focus on all type of defects, also because there are too many. We just took a representative one for the Forsterite. You're welcome. Wilke, thank you for the nice talk, Dario. Thank you, Wilke. I have a suggestion for investigating the curve structure on the substrate with the vacancy. You could either look at the Bader charge or even better make a charge density difference plot. Then you might see that the pi electrons are transferred to the surface. I actually have done that, not just with Bader, also with other charge methods. We actually saw that there is a transfer between the PAHs and the surface. Thank you, Benoit. Tour guy, sounds amazing results. From an astronomer mindset, can you please tell me about limit temperatures we can observe those PAHs in ISM? For example, the ISM temperature in Milky Way varies from 10/6. So in which specific region we expect to see more PAHs? At what temperature we cannot even have PAHs stable? That is the curious thing about PAHs. PAHs basically can be everywhere in the universe, in all kind of regions, because sometimes they also can be cations, perfectly neutral. For sure, we cannot see PAHs at higher temperature, as you suggested, over 10/6 Kelvin. So we focus on photodissociation regions, specifically in the range of PAHs between, let's say, 100–500 K. I hope that yes, you're welcome, tour guy. Dana, could you apply your DFT work to understanding how mineral surfaces could contribute to the formation of complex organic molecules? Of course, I can do that. With DFT, we can also study their activity on just the bearing surface. You're welcome. Any other questions?
Okay, so if there are no other questions from the audience, I'm gonna go ahead and pull up the concluding slide.
Okay.
Okay, so thank you so much again to Dario for the excellent talk today, and our audience, as always, for joining us and asking thoughtful questions. Just a quick reminder that there is the AVS 2020 International poster competition. So be sure to register by July 6th if you are interested in participating and taking a shot at winning that $500 cash prize. And coming up next week, we have our final talk of the webinar series by Dr. Niels Ligterink from the University of Bern, and he's going to be talking about searching for the chemical fingerprints of extraterrestrial life. So be sure to join us again next week for our final installment in the series, and we'll see you guys later. Thank you, Dario.
Thank you, Kate. Bye.